Hello, Lecture 5, Analog Electronics, Test and Debug. Specifically, most of this talk is going to be about the tools that are available for testing and debugging your analog and analog digital circuitry, because you will need to do both at some point, I'm sure, and how to use them and and all these different things that are available to make your life easier. So specifically, I'm going to talk about these different tools here. I won't go through the list, and we'll look at those. And just the main point I want you to take away from this is that these tools exist. The specifics of what make they are and how they work. I'm going to leave you to read the instruction manuals and whatnot. The main point to know is that they are available and the sort of things that they can do in order to make your work better. So in the simplest case, I mean, I hope a lot of this will be a repetition for most of you, but it's worth saying anyway. So in the simplest case, we've got amps, volts and ohms. So otherwise known, you'll hear people sometimes talk about AVO meters, amp, volt and ohm meters. So in other words, current, voltage and resistance. And so there's all sorts of different types of those. As you can see here, there's pretty old devices. That's sort of my physics from the early 80s. But modern stuff now, very good equipment, often known generically as digital voltmeters, and often known a bit like a biro by the common trade name, which is a fluke. And these are fabulous pieces of kit. Measure those quantities very well. Some of them also measure things like frequency as well. And as you can see here, but designed to be ruggedized and used in an industrial environment. So even the obvious voltmeters and fluke come with a little bit of warning to them. So one of the things you'll usually find out is 90% of the time you'll be using these devices to measure volts, whether it be power supply or a data line asserted and things like that. Sometimes you'll measure them with you'll measure resistances with them, and also very occasionally measure current as well. At which point it's important to note these devices, you then have to move the lead across to these amp settings here. And the important thing to remember there is to put it all back when you finish, because it will catch you out and you'll wonder next time why your voltmeter suddenly stopped working. You've left the lead plugged into the wrong socket. They also come with internal fuses, so if the thing's died there, that's the first thing you should check before. The second thing after checking that the sockets are correctly configured, check the internal fuses before you throw the thing in the bin. But yeah, nice, all sorts of different ranges that these devices work on, and different quantities that they can measure. So, as I mentioned, you will occasionally measure current using the ammeter function of your DVM, probably a lot of the time, and that can be a bit of a pain sometimes, because typically you have to break in and put your meter in series with the load and source, and that can be annoying, especially if you've got very thick cabling or something like that, or the current that's going down that wire is very, very high. So because of that, in the last few years, and this is something that's come along since I was a student, current clamp meters. These are rather smashing device that clamps around a conductor, and it exploits the inductive effect of an AC current, so of an alternating current, to detect how much current there is flowing in that conductor. Now, modern equipment apparently is also capable of measuring DC as well, using a slightly different Hall effect, I think. I need to look that up. But generally, these large-scale industrial ones can measure current flow reasonably accurately in an industrial environment. Not quite as accurate as an inserted in series ammeter. but as you can imagine, very useful piece of kit. So now something that I hope everybody here is already intimately familiar with, an oscilloscope. We'll be using them in the labs. So that top one there in the picture, that's that's a cathode ray oscilloscope, as I used to know it, with which it could only display a repeating signal, things like that. Generally being entirely superseded these days with what are often known as DSOs, digital storage scopes. So that's obviously what the ones that we've got in the lab here. So just be aware that when people talk about DSOs, there is a slight difference to what sometimes people call CRTs, cathode ray oscilloscopes, CROs. Now, yeah, as I mentioned here, what an oscilloscope really does is it plots voltage against time, and different price pieces of equipment, usually trading off the amount of time that they can record or display against the bandwidth as well. In other words, the resolution, the time, and the time increments at which they can sample. So very expensive oscilloscopes might be able to sample way down into the nanosecond sampling period and things like that, deeper than that. And so that's generally where your money goes, is they're capable of much greater bandwidth. And they also they're less intrusive on the electrical signal. We'll talk about that in a second, what I mean by that. So as I mentioned, an oscilloscope fundamentally measures voltage against time. So quite often you'll be in a situation where you're trying to measure something else. And so in that case, you're going to be putting some sort of transducer, which is a device that translates a physical, any physical quantity into an electrical signal. In this case, it's the same voltage. So the classic one you'll often see is people put a speaker on the end of their oscilloscope, and that will generate a tiny voltage, which then we can display. And the other one is you can measure a current flowing in a circuit indirectly by connecting our oscilloscope across a small resistor, usually, so you don't cause too much interference with the circuit in that circuit, and then we measure the voltage across that. So in other words, we're always trying to derive a voltage from another signal that we might be interested in. So bear that in mind, and the way that you derive that signal can be quite important, because the derivation process can introduce a corruption to the information you can be looking at. So just hold that thought when you're using an oscilloscope. And as I mentioned a moment ago, also be aware of the shortcomings of an oscilloscope. Like any piece of equipment, generally when you try and measure a physical quantity, that piece of equipment will tend to interfere with it, Mr. Heisenberg and all that. And we've looked at this a lot so far in the course, but I'm sure you're all familiar now that wherever we put a piece of kit, generally there are unwanted resistances, capacitances, and one thing that isn't shown in that diagram is inductances as well. The very length of wire that we have from our probe coming out of our oscilloscope can cause a corrupting effect. And so here we go, we can measure that signal. We're looking at something there, and of course we've got to bear in mind that potentially some of that corruption, some of that ringing we're seeing there is due to the very scope that we're connected to. Cast your mind back to that anecdote I gave you in the previous lecture, the one about how I got the corruption where ironically the CMOS gate was overshooting the very action of putting my oscilloscope probe on that signal in order to investigate it, was curing the problem slightly. So is that a corruption or a fix? I don't know. At the time it felt like a corruption. So be aware, your oscilloscope, the very action of connecting your oscilloscope is introducing these resistances and capacitances. And generally more expensive oscilloscopes are designed to have very, very high input resistances and very, very low capacitances associated with them. So in other words, they are doing as much as possible to show you the real signal that's happening there without interfering with that signal. So as you can see here, typically we're talking about 1 mega ohm, and devices, and a perfect device would have an infinite input impedance, and tiny amounts of capacitance as well that need to be eliminated. It's still present though and could cause an effect. Watch out for that. So we're used to seeing those oscilloscopes on the bench. Now this is something that has come along in the last few years, and I think they're absolutely tremendous. So this thing called the Picoscope is just one example of a whole range of different low-cost oscilloscopes that are out there on the market now. And generally they're just a pod that plugs in through a USB port into your existing computer. They're exploiting the fact that most of the cost of an oscilloscope that you put on your bench is that screen and the processor and everything like that. And you've already got one of those sat on your desk inside your laptop. So we can afford just to create an oscilloscope by plugging these devices in. And they're very cheap. I'm not sure what the Picoscope costs, but I had a look on Amazon the other day, and its competitors cost about 50 quid, which is a phenomenally good price. So you're talking at something that previously used to cost thousands of pounds, is now coming down to tens of pounds, and so you can have your piece of equipment there on your desk very easily and very flexible. Probably not quite as effective as a £10,000 oscilloscope, but for most sort of work that we're trying to do, like for example the coursework in this course, perfectly adequate, and right there in your bag if you need it. So that's oscilloscopes, and I'm sure I hope everybody's familiar with oscilloscopes. Probably less familiar with the concept of logic analyzers. I know some people here are familiar with logic analyzers, but oscilloscopes and logic analyzers complement each other brilliantly when developing this sort of equipment. And so I just want to introduce you to what a logic analyzer is and how it complements an oscilloscope as well. So as you can see here from these displays, the display looks a lot like that of an oscilloscope. And the first thing you notice is that it's got a lot more signals being displayed. So in other words, it's got where an oscilloscope might just have 2 probes attached to it, and a logic analyzer typically can have 8, 16, 32, even more sometimes. So in other words, it can capture a much wider signal rate, set of signals coming in. There is a trade-off, because it doesn't measure voltage precisely. It can only distinguish a digital signal, in other words, above or below a particular threshold, which is often programmable. So in other words, all we need to know is whether it's high or low. And obviously, as long as our digital signal is working correctly, and we can use an oscilloscope to establish that, we can then switch to using a logic analyzer to gather a whole series of information streaming in from our circuit. And so you can imagine that's very useful if we're developing a serial link, or better still a parallel link, or a data and address bus from a microprocessor, a memory interface or something like that. So in other words, where an oscilloscope has a few very high resolution probes, a logic analyzer has lots of low resolution ones. It can only resolve high or low, where an oscilloscope can resolve to many, many different levels. So, as I mentioned, lots and lots of probes coming out, and they usually come in what are these called pods. Plug on the end here, and they have nice little clippy things often, which always get lost. And so, along with great power, as always, comes responsibility, and you can end up with a real mare's nest of signals attached to your circuit. So it does require a wee bit of management, making sure you've got everything connected up correctly, and connectors aren't dropping off. All sorts of things can go wrong like that. Can get quite frustrating, but once you've got your Analyser hooked up correctly, it provides you with a wealth of information on how to debug your equipment. Very powerful, very, very useful to have with any digital device. So again, just like with the Picoscope that we were looking at, there's a whole series of low-cost logic analyzers available now, and just in the same way that there's many different oscilloscopes, one of which is Picoscope, there's this device here called the Saleae Logic, which I think is a tremendous piece of kit. Costs about 50 quid. As you well know, there's this Chinese knockoff on Amazon for a tenner. Not quite as well made, but does the job for most of the sort of things that we want to do in the lab. So this is very much the logic analyzer equivalent of our low-cost oscilloscopes that come along now. So in the old days, logic analyzers were eye-wateringly expensive, even more so than oscilloscopes, because they tended to be lower volumes because of a bit more specialist kit. But now it's the same old trick where we have a pod here that plugs on to our PC, which does all our processing for us, and all the logic does is really gather the information quickly and buffer it back to the PC and an application running on the PC. And that's how they managed to keep the cost down to about 50 quid for something that used to cost thousands of pounds. So look out for those as well. So this really is a golden age compared to the sort of equipment I was using when I was an undergraduate, because for a hundredth of the cost and a fraction of the size and weight, we can all have our own equipment and we can carry it around with us in our bags, and so we can work at home or wherever it's convenient for us. And we're not all squabbling over kit like that. So well worth looking into and being aware that sort of equipment is available. So as I say, most of I'm talking about Saleae Logic as an example again, but again you tend to get an application running on the PC here. Here it is on my PC on my desk. And so this particular version, as you can see, it gathers the data, streaming in off that pod and displays it. And really what I want to show you here is all the sort of features that are available from that sort of application. So very nice here. What's this arrow here is the result of me just hovering my mouse over that gap there, and automatically the application will check the width and the period and everything, all these different values. So we can inspect the signal very quickly, very easily, without having to move cursors and things like that. So tremendous flexibility built into that software, which you just download for free off the web. So very useful equipment, very quick to work, allows for very quick debugging and understanding of our signals that are coming out of our digital circuit. So because there's so many signals as well, we've got this complex data analysis capability within the PC that the device is plugged into. So it's useful just to be aware of some of the excellent features that a logic analyzer is capable of. The first one is triggering. I mean, we're used to, on an oscilloscope, changing the trigger so that the signal latches each time that the signal goes high. The logic analyzer allows us to take that a little bit further, and we can configure an exact sequence and also an exact pattern in parallel across several devices. So we can sit there waiting for a particular thing to happen and then start recording automatically with that. So in other words, we can have these very elegant and sophisticated triggering scenarios that we can set up. Say if we're looking for a particular scenario that just happens once in a while when a bug happens or something like that, we can leave the device sitting there waiting for our particular error condition to crop up, for example, and gather the situation. And weirdly enough, it can actually look back in time, because of course it's recording all the time into a circular buffer which freezes, and so we can actually look at what the signal traffic that was occurring both before and after that very special triggering event. We can also usually configure how we choose to use our logic analyzer's resources. And generally, as you can imagine, there's a certain limit on how fast the device can record its data from the logic analyzer. And there's also a certain amount of memory in the device so it can remember. And we can trade these two off. Obviously, we can either log data at a relatively slow rate, at which point the memory will last longer, or we can go fast and short as well. And there's usually tools built into our logic analyzer like this one for the Saleae, but it allows us to trade those two off. These tools can go a step further as well, and we can have levels of decoding and intelligence built into the logic analyzer, so it actually understands the basics of the signals that are coming out of the device. So that in the simplest case, we can decode a parallel bus. We might have, say, 4 wires, and we can display them individually as 0 or 1 on those 4 wires. But most of the time, if that's a bus, we will want to consider that as a 4-bit bus, at which point the logic analyzer is quite capable of effectively merging those 4 signals and decoding them from any and displaying, instead of the individual 0s and 1s, we could display any number from 0 to 15 or f hex. And that's very powerful here. It's an example of it in this slide here, so have a look at that. Also, a lot of logic analyzers are capable of decoding serial lines. So a serial line will typically have a standard way of transmitting information. So it'll have a start bit, say, right, this is the beginning of my data. Then there'll be data at a certain data rate, and then some bits at the end to say this is the end of the data. We can load software into our logic analyzer which can decode that and actually extract the serial information by looking at the timeliness of the signal that's coming on. So you might only be using one logic analyzer input there, but doing some quite sophisticated time-based decoding in that instance. And perhaps most sophisticated of all is what's called a disassembler, where the device can actually, say, be monitoring the instructions that have been read in by a microprocessor from its memory, from its binary executable in memory. And if it can see both the data and the address from which that data has been extracted, it can actually see those instructions being loaded and decode, if it's got enough intelligence built into it about the instruction set of that microprocessor, in order to actually understand which instructions are running inside the device. So you can imagine that requires quite a sophisticated understanding built into the logic analyzer of the microprocessor's instruction set. But the prize that we get for that is an actual display of the very instructions. We can see what the microprocessor itself is thinking. It's a thing called a disassembler. So in other words, it's tracking the very instructions being loaded into the device's memory. That's getting harder and harder these days as modern microprocessors tend to cache their instructions internally. And so that there's other solutions to that sort of thing that we're going to look at in a second. Disassembler, though, very powerful, very sophisticated technique built into logic analyzers. So, as I've hinted at already, it's important to understand that logic analyzer and oscilloscope, two complementary tools, just like your hammer and your screwdriver, both good for what they're good at, but you wouldn't want to be stuck with only one. So just to recap, oscilloscope, narrow and precise, couple of probes usually, but capable of measuring down to sometimes millivolt, fraction of millivolt resolution. Logic analyzer, wide but imprecise, only capable of distinguishing high or low. So in other words, if we've got a data bus that was being corrupted somehow, So we've got some stray capacitance due to the effects that we've been looking at already. The obvious tool for the job is our oscilloscope. In fact, looking at it with a logic analyzer would be downright misleading, because if we got a glitch, a temporary glitch on a digital signal, but we looked at it with a logic analyzer, all we'd see is a transition to high. We wouldn't actually get any indication of, say, ringing or all the effects that we've been studying in this course. And so your logic analyzer allows you to look at a higher level, the meaning of the digital signal, while it's deliberately losing or throwing away the information about how that signal is actually transmitted. So the analog effects need to be inspected using an oscilloscope. And so you have your oscilloscope to satisfy yourself that the information is being transferred correct, or the data is being transferred correctly. And then your logic analyzer sits above that, confirming that the data is meaningful. In other words, the data is useful information being transmitted. So hold those two thoughts, and bear in mind which tool you would use for which situation. There's also equipment out there now called mixed signal oscilloscopes, which is a little bit of both really. And I think this diagram here gives it away, in that yes, it's exactly what you'd imagine. It's both a logic analyzer, it's a handful of logic analyzer probes and a couple of oscilloscope probes, all built into the same device. So you can imagine you might be in a situation where, oh, there's a funny glitch happening once in a blue moon, and so we might use the logic analyzer to track the high level case and maybe perhaps trigger a recording when this strange event starts to happen. And then we want to actually record the analog signal to try and find out why that event is happening. And so mixed signal oscilloscope. Never used one myself. Be very interested to look in the market and see what's available there. I have seen that the Saleae device, the logic, I believe that they're going to have a similar piece of kit to this available as a podded thing in the next couple of years. So something to really look out for. That could be a very useful tool when you're debugging a corrupted signal, which is exactly what we've been talking about in this course. So the next thing we're going to talk about here is, I say JTAG. The JTAG is a little serial port that goes on gets built into pieces of electronic equipment. Usually it appears as a tiny little header integrated onto a device somewhere. And it's important to understand that the JTAG port itself isn't in itself a piece of debug equipment. It's just a gateway, an entrance connector to allow various debugging and test capabilities that are built into the silicon and onto the board itself to be accessed. It was originally designed and implemented with the intention of implementing boundary scan. I'll explain what that is in the next slide. But the usefulness of JTAG, the main point about it, is that it's so unobtrusive, it requires little silicon, doesn't need any software to run. It's allowed all sorts of other things to be connected up and all sorts of built-in test equipment to be accessed. So let's have a look at that. I mentioned boundary scan. Right, what on earth's that? And this really goes back to trying to resolve a problem that came along as chips got more sophisticated, and these inline devices that we're familiar with, where we could place a probe on a particular leg and find out what was going on in there to check that, say, it was connected up properly. How on earth do you do that with these array type chips that came along in the last 20 years? Oh, 30 years now. And the problem was, of course, you couldn't get your scope to it. You couldn't get your scope probe to it. So there was built-in test equipment included into the silicon itself. So in other words, the equipment under test contained effectively support for this equipment. So there's a tiny capability to suck out the actual highs and lows that are visible on those grid arrays there. And so it created a sort of virtual scope probe that can be touched down. And so the wonder of the JTAG port is that because, of course, you couldn't get any software running potentially, because if, for example, you hadn't soldered your chip down properly, so the clock wasn't working or anything like that, there was no use trying to get any test software running on your chip because it wasn't there yet, or in fact the chip might be so simple it doesn't use software. So the idea of the JTAG port is entirely clocked from the external equipment. Very little, there's no intelligence per se, it's just a very simple piece of logic to allow this information to be extracted out, the boundary being the actual chip legs itself, the states of the actual inputs and outputs to the chip. And so yes, you can see what we're trying to do here is create a capability and yet another PC-based tool to effectively measure highs and lows and check continuity generally, to check that chip has been soldered down properly and the signals have been passed to it correctly. So the closest thing we can get to putting an oscilloscope, well, more like a logic analyzer to be honest, because it's generally only got high-low resolution. But a good workaround to this ball grid array problem. Now, as I mentioned, as well as boundary scan, we can also connect up other test equipment and development equipment via our JTAG port, amongst other ports as well, but typically one of them is a debugger. Now, a debugger is a wonderful piece of kit. I have to declare an interest here. I spent 3 years of my life writing debuggers at ST in the late 90s. Very useful piece of development equipment. What is a debugger? It allows you to execute a program and then install what's called a breakpoint, which informs the microprocessor to stop executing that particular program at a very particular address in memory and signal that execution is halted out to the outside world. And generally there'll be a piece of test equipment out there that intercepts that signal, and then that can then go in and inspect the state of the device's memory and decode it using what's called a debug table, which gives you the definition of all the different variables and where they are inside the device, and allows us to actually look into the brain and understand the thoughts of that machine. So it's the sort of functionality which to a large extent can be inserted by a whole series of printf statements. But what happens if printf isn't working? And also a debugger can allow much more precise inspection of particular events going on. We can check when things are executing and things like that. Now, a typical debugger runs on a PC potentially, debugging code is running on the PC, but for this course I particularly want to raise your attention to the concept of remote software debuggers. And we've already looked at how we can download an executable after it's been compiled onto a target device, but we can also communicate with that target device with debug, and by enabling pieces of debug equipment that are usually built into the actual target microprocessor, we can actually perform debug on a machine that's operating on the other side of the room. And we can look into the mind of this target device, which is executing over there with no screen or keyboard or anything like that. We can actually understand what's going on. So here we've got an example of somebody set a breakpoint and we've checked and it's stopped executing when it's hit this particular line of code to find out what the variables are. For example, we could understand exactly why the device had entered that particular set of code, set of instructions. So all these tools I've been showing you about are showing you as you can see, they require a certain level of integration. So we need to provide support to connect them up in the simplest form. So when you design your equipment, bear in mind that you're going to be using this equipment. Almost certainly nothing works first time. And even if it does, you need to prove that it works first, that it's working. So, good example. Firstly, put some little links and headers on here to allow your scope probe or your logic analyzer scope probe to be attached. You can also put nice headers on as well, so we can just push those connectors down onto it, so that this could be this could be connected to a logic analyzer or an oscilloscope or whatever you want. But it makes for very, very quick and easy debugging. Now, if you develop a PCB and you've got separate parts of that PCB, why not design in some little jumper links that you can completely shut down one part of the PCB and develop just the other without, if there's a suspicion that the two might interact with each other. We can also depower things using links and things like that. And if at the end of the day you don't need those links anymore, fine, you can take the headers out and just put a soldered link in there instead. But that will give you the flexibility you need to configure things quickly and easily without damaging your circuit or interfering with the signal during your development and test. So it can get simpler than that as well. Good idea is sprinkle a few LEDs around as well. So the simplest form here's something I knocked up at Airbus a couple of years ago. There's a little light here just to show that the thing was switched on, because the worst thing in the world is you plug your piece of equipment in and you don't even know whether the power's on it or not. Because sometimes that power will be coming from some distribution panel, which might be the software control, anything like that. And when there's just a resounding silence going on, the first thing you want to know is it switched on? Surprising. Now here's a piece of kit from Nigel. It might be all covered in dust and looking a bit tired, but he's put 7-segment display built into the middle of it. Very simple to drive in software, but very powerful, because you're going to be able to send all sorts of little messages, error codes and things like that. And also, you might like to include little LEDs, lights to flash on and off from software internally. Or this one shows that the thing is actually powered on. That one can be driven from software. So it gives a very pleasing feeling that the thing is alive in there. And it's surprising how much information you can signal out to the outside world, but just by an LED. So for example, you might have it on all the time for one state, flashing slowly under some conditions and flashing quickly under others. So there's 3 states already. 4 if you count off. So when you do your design for test, think about JTAG ports as well. JTAG, as I say, was designed specifically for supporting test equipment. So the first thing you see here is that these headers are very small, very unobtrusive. And the second thing to know about is you only need one JTAG port for the entire board, because the JTAG protocol, as you see from this diagram, allows devices to be chained up, and the test equipment, which automatically will latch the data through other chips in the way to access. So potentially this device can talk directly to device 2, but having its information clock past device 1. Very useful. JTAG always useful, and it can be, if designed properly, can be very low impact on your circuit. So, what do we learn? The key point is there's a lot of tools out there, and be aware that they exist. Familiarise yourself with all those excellent tools that are available. There's others that I haven't mentioned here as well. As you can see, they're all different horses for courses. They all have their role. So choose which tools you need. For most development that we'll be doing on this course, Logic Analyzer and Oscilloscope Very useful indeed. And I think the main point though is that third bullet is when you design your equipment on the assumption that you'll be needing to connect test and debug information, debug equipment to it. And it's very easy to do if you think about it ahead of time. A few headers, a few LEDs, a few connectors here and there. You can always dispense with them in the second spin of your PCB, or just blank them out and leave them not, or leave them not fitted. But if you design them in from the ground up, it'll make your life a lot easier when you come to bring up the device. No. Okay. Hope that's been useful. Good luck with your debugging, and see you soon.